Hey, what's up? As I've done other times around this year, we're gonna make a major format switch for this channel. I've been thinking about it a lot. Manga is fun, don't get me wrong. I do enjoy manga, but am I learning? Am I actually developing a more profound and meaningful understanding of the world I inhabit? Is Kaiji One Poker Hen teaching me about probability? Is One Piece teaching me about the history of piracy? No, no. They're just entertaining stories. And that's fine, but we gotta be smart with how we use our time. And I think it's wise for me to change this into an educational learning channel. Let's Learn, where you accompany me on journeys into obscure knowledge and complicated subjects, and basically we're just going to slam our heads into the wall until they make sense. So our inaugural subject is Hawking Radiation. Ooh, well, this is an exciting one. I'm really hoping that by the end of this video I will actually understand what's going on with this. So I've been reading A Brief History of Time, because Stephen Hawking recently passed away, RIP Stephen Hawking. And it's a book that when I was like pretty young, like in my early teens, I read just kind of to say I had read it, because I knew it was this like really famous intellectual book. And I can remember kind of just being mind blown by what I was reading and kind of understanding vaguely the implications. But for the most part, everything was just sailing like right over my head. So when he died, I thought, okay, this is a good opportunity. I really want to actually understand this book, because it is written for the layman. He did go out of his way to make it accessible and understandable, and I think he did a really good job. And I find that now that I'm reading it with a goal of complete comprehension, excuse me, taking it slowly, really kind of checking my understanding with each new subject, I'm so impressed with how he was able to talk about such complex subjects in this like nice chronological causal format, where he'll pick something complicated, he'll break it down using analogies, he'll go through all the steps that people took to discover it and come to a complete understanding of it or whatever. And he kind of has some fun with it too. So I really recommend everyone check out this book. So I think I'm making pretty good progress. I think I get almost everything, but there was one part where I just kind of had to give up and move forward. And it was something that I had like talked to some friends about, and they tried to explain it, and it helped a bit. And I read like a couple other articles about it, and that helped a bit. But I still feel like I'm not quite there yet, and it's become like a low key obsession. So I want to figure it out because it seems important. It's the one that's named after him, Hawking Radiation. All right. So first off, let me break down what I think is going on. Okay. So we'll get as far as I am now, using entirely my own understandings. And then together we'll start going through the internet and maybe watching YouTube videos or whatever it takes to figure out the really mysterious parts. Okay, so the first thing I think I should explain is gravity, or like the version of gravity that matters to us. This is Gravity is still, I think, pretty mysterious in general, but there is a way to visualize it that I think will help us understand what's going on here, that I don't think will lead us to any like inaccurate misunderstandings. So this grid, I'm going to say, is space-time. It's a two-dimensional representation of space-time, which is actually, of course, a kind of five-dimensional thing, because there's like imaginary time too, but we don't really need to worry about that. And what you can think of massive objects as doing is like, am I going to be able to draw this very well? I can picture this really easily in my head, but I don't know if I can draw it too well. So this is like sagging into the third dimension, okay? And this is like a star or whatever. So it's like it's kind of dragging and pulling, if you think of like a ball in a net, dragging it down. And particles are just trying to take the shortest possible path through this. But what that ends up meaning is that if it's curved, the shortest possible path through the curve involves like taking the curve, and that's what leads to like orbiting effects. You can kind of imagine Earth is just trying to move straight, but because it's moving straight on this curved surface, it ends up rotating the star. Okay? And the more massive something is, the more attractive it is gravitationally, the more it like sinks down. Okay? Does that make sense? I hope that makes sense. This is kind of awkward. I have to like keep expanding. Okay, so when stars get really, really big, eventually it's such that the mass on the inside, like it keeps kind of compounding on itself. The outer reaches collapse inward, and you can get to a point, depending on kind of the initial conditions and whether the forces that make atoms push apart, the nuclear forces and the electromagnetic forces, can sometimes even be overwhelmed by this. So things have no pushback anymore. Everything just collapses more and more and more into a non-existent point called the Singularity. And this is like so these just go forever. It's like if you can picture this being like a curve, this is sort of like an asymptote. It has infinite curvature at this point. Or like not even at this point, there is like no point. It just hits this point of infinite curvature as it approaches the center. So this is a black hole. You can kind of picture this like cone-shaped tube. But of course it's not two-dimensional. You have to picture a drain in the 4 dimensions of space-time, which is kind of hard to visualize. So the fact is that this hits this kind of like infinite curvature means that really weird things start happening. And it's these weird things that I can't really get my head around. And one of them, and this is what leads black holes to have their name, is that photons, which are the fundamental particle that light is made of, won't even escape. So normally light moves so quickly and is so light, is so unmassive that something like a star, light particles will bend around it in space-time, but they won't ever get slowed down enough that they actually get pulled back into the star. But black holes are so massive that it actually can't escape, which is why they're black. You can't see them. So if photons can't make it out, you would be right to think that absolutely nothing can make it out. And there's this part, the event horizon, which is basically like past this, the gravitation is so massive that there's absolutely nothing can come out, which is why it's so hard to kind of talk concretely about what must be happening in there, because there's no way of ever observing anything that's happening in there. Anything you sent in to observe it could not possibly send out its observations. Okay, does that make sense? So I made it really big, but we can just kind of scroll around. So this is gravity. Next thing we got to talk about is vacuum flux, or vacuum fluctuations. So this is on a very macro scale. Now we have to go to the exact opposite side and talk about things happening on a quantum mechanics level. So in quantum mechanics, there's the uncertainty principle, where things will simultaneously act as single particles flying through the air, photon, but then at the same time, they also exhibit properties of like a wave. So the photon is like both a singular particle, which has some tiny minute amount of mass and some energy and is traveling at the speed of light all the time. And at the same time, it's also exhibiting properties of this wave, that it has like crests and it like cancels itself out if a crest happens to meet a trough. And it'll like spread out like waves do when it hits certain slits and stuff. There's the famous double slit experiment. But because it's constantly in both of these states, there's the uncertainty principle, the famous Heisenberg's uncertainty principle, where we can't ever for sure know both its exact position and exact energy, because making an accurate observation of one of them involves like setting as a frame of reference the other one. So like as our certainty increases of how energetic it is, like how fast it's moving, our certainty of where it is at that time decreases. That's pretty complicated, but we don't really need to understand that. But what it means, and this is like a pretty crazy aspect of this. So if we just have like empty space, there's seemingly nothing here. There's no atoms. There's no molecules. There's no stars or galaxies or anything. Just a little cube of empty space. We feel like we should be able to say, okay, the energy in here is 0, and the position of anything in here is 0, right? But then that violates the uncertainty principle, because we should never be able to make a conclusive statement about both energy and position simultaneously. So somehow they figured, this is one blows my mind. Theoretically, they worked out that there must be something going on there to create this constant energy flux, that even though the whole thing averages out to 0, once you get to the minute quantum level, there's actually all these tiny little things happening that makes it in this constant state of flux. So what they figured out was happening, and they were actually able to observe this, is that spontaneously, I don't know how, but particles will just pop into existence, okay? But because we can't have a net increase of energy, it always has to be a particle and its anti-particle pair. So if this is like a photon, then the other one that pops into existence simultaneously has to be an antiphoton. Okay? Which is the negative, the antimatter partner of this fundamental particle. And like photons can pop into existence, quarks can pop into existence, gluons and stuff, all these crazy fundamental particles. And then because they are opposites like this, they immediately collide and annihilate. They zoom into each other pretty much instantaneously, and then as soon as they're there, they just like poof out of existence again. And they call these virtual particles, which I think is a very confusing name, but that's the term they use, because for most intents and purposes, they don't exist at all. The annihilation, so yeah, they slam into each other, and then they're just gone. I can't really draw gone, but they're gone after this. So it leads to this. So, yeah, most of the time that they have been detected using this crazy experiment where they have two. This isn't actually necessary to understand. Well, maybe it is. This part just confused me more, honestly, about Hawking radiation. But the experiment itself is cool, and I think I can explain it. So it's like, this is happening everywhere in space all the time. But they were able to set up in a lab these two reflective plates um, so that when photon and antiphoton pairs appeared here, how did it work? It's like some subset of them would bounce off the plate, like as soon as it like spawned, and then because they would like bounce back and forth, some of them would cancel out. And because then there would be like less photon antiphoton pairs happening here than outside, where it's like more concentrated, because it doesn't have this like canceling out of wavelengths, getting rid of a bunch of them. There's like a force being applied by this denser area on the less dense area, and they were actually able to measure that, and it aligned with like their predictions and stuff. So this was the experimental proof that this is something that's actually happening, which is pretty cool. And then as a consequence of that, if we say that in this area E equals 0, like there's net 0 energy and all of this stuff, then this is where things start getting really screwy to me. You can say that the energy in here is like negative some amount, because it's less than 0. There's less energy in here, and this energy we define as 0, so this is negative energy. Okay, I don't really get it though, because there's still energy in here. There's still stuff happening. So how does it have okay, anyways. Okay, so so you can kind of come up with experiments like this to interfere with this process of quantum flux and stuff just poofing in and out of existence all the time. The other circumstance where this thing kind of gets messed with is on the event horizon of a black hole. So we have, this is our event horizon. That's event horizon. You know, where absolutely nothing can come back from. So if our little photon antiphoton pair pops up here, and it just so happens that one pops up on the other side of the event horizon, it can't go and annihilate itself. It can't cancel itself out. This one gets sucked into the black hole, it gets trapped, and then because this one isn't attracted to its buddy, it'll go flying off and just like continue existing. Okay? So what this means is that functionally the black hole is shooting off particles. It seems like it's radiating them. Okay? And this is Hawking radiation, these particles flinging off. But the other thing that this leads to is that the black hole like actually shrinks. Okay? As this is happening, the black hole slowly is shrinking. Now, I think this has been observed experimentally, but right now there's like microwave radiation everywhere in the universe as a remnant of the Big Bang. So black holes are always like eating more than Hawking radiation is giving away. But in the far, 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 far future of the galaxy, of the universe, like quadrillions of years from now, eventually all of that background radiation is going to settle down and black holes will start overall shrinking. This is the prediction of Hawking radiation. So why is it shrinking? Okay, which I think this is kind of an obvious question. Because something is going into it, something is getting eaten, shouldn't it be growing? And it's like nice that it just seems, for all functional intents and purposes, it's just radiating particles. Particles are coming out, and then it shrinks. It's like, nice. That adds up. But what's like actually happening? So it comes back to this negative energy thing that because there's like more. Okay, this part is where I'm starting to reach a little. This part is where I don't really get it, but this is like my best understanding. Is that again because we have a lot of stuff going on here, all this like quantum flux, and we still say that this is like E equals 0, okay? But now this guy is just been released into this, so that seems like it should be like E equals 0 plus 1, but you can't do that. You can't just spontaneously create energy, all right? So the negative one has to be this guy. So this guy actually has negative energy, okay? What that means is, I don't know. Negative energy is just, I think, really fundamentally unintuitive, and it might be the wall that we hit in this little let's learn adventure that we just can't climb over. So it has negative energy, and because of this bad boy, which I'm sure you all know and love, it was in Dr. Stone. It's on Senkyu's shirt. Actually, beforehand I was like, manga's not educational. Dr. Stone teaches me a lot, so I can't even continue with that facade. Okay, so the energy equals mass times the speed of light squared. So our mass here is -1. No, wait, I'm sorry. Our energy here is -1. Okay, and then you like rearrange, and mass like goes down. I'm not actually gonna do algebra. Don't do algebra on camera. So mass decreases. Something with negative energy hits the black hole, and it becomes less massive. I don't get it. This is the part that makes no sense to me. So I don't know. Does this make sense so far? We have, and the point of this, like trying to really conceptualize the fact that space-time hits this infinite curvature in the black hole. All I'm saying is that it's weird. It's what's called a singularity, where it's like if we have kind of some function or whatever that we can kind of like observe things about. We can kind of like understand the properties, maybe predict it. There can be points, like asymptotes in graphs. I didn't leave myself enough space to do it. Where it's just like, huh? And if we're kind of like living in this universe, when it hits whatever singularity, or like this one, you know, this is sort of like a more conceptual, analogous type thing, where basically there's nothing we can observe about what's going on here that can at all help us with what the hell is going on here, right? So the black hole is also like a singularity like that, where it just, nothing really makes sense. But I want it to make sense. I want to at least give it my best shot to understand what the hell is actually going on here. So let's dive in. Let's start by Googling Hawking radiation. Electromagnetic radiation, according to a theory, should be emitted by a black hole. The radiation is due to the black hole capturing one of a particle-antiparticle pair created spontaneously near to the event horizon. Nice. Okay, so I feel like I get it. Hopefully that brief definition makes sense to you based on my lovely notes. Find Hawking radiation explained this way in a lot of pop science treatments. Uh-oh. We gotta go beyond pop science now. So the Wikipedia article I've already looked at. Here. This is what I was trying to draw before. The space-time lattice analogy. So you can see space-time gets curved around heavy things, and you go like, whoa, I'm going on a little curve now. Because I'm trying to go straight, but straight's not straight anymore. Okay. So there was Uh... Okay. This is the paragraph that describes what we think is going on. There's like a couple explanations. So this one's saying, should I zoom in a bit for ease of reading on the video, maybe? Sure. There's less text on screen too. It's like less overwhelming to try to figure out what I'm reading. Classically, the graviton generated by gravitation singularity is so powerful that nothing, not even electromagnetic radiation, can escape from the black hole. Unknown how gravity can be incorporated into quantum mechanics. This is a big problem. Nevertheless, far from the black hole, the gravitational effects can be weak enough for calculations to be reliably formed within the framework of quantum physics. Blackbody radiation. Humanic radiation is produced as if emitted by a black body with temperature inversely proportional to the mass of the black hole. By imagining the particle, any particle, boosted by the black. So this is kind of similar but different. Here, instead of it being like one guy, it's like generated right on the event horizon, and one guy's like, it's too late for me now, and dives right in, and the other one's like, I'll live on in your stead, and flies off. This theory is saying that it's like happening right around here, and normally they would like fly into each other and annihilate, but instead the craziness of gravity like launches them so far apart that both of them become real particles and fly off. This makes even less sense to me, because then it's like the black hole isn't involved at all, but it's still shrinking. So why is it shrinking? I don't know, but let's... this is this alternative view. This is the one that Hawking himself puts forth in Abhot. So I feel like we gotta go with this one. It's Big Daddy Hawkins telling us that this is what quantum or Hawking radiation is, so we gotta believe it. Vacuum fluctuations create a particle-antiparticle pair to appear close to the event horizon of the black hole. One of the pair falls into the black hole while the other escapes. Yeah, alright, ready? In order to preserve total energy, the particle that fell into the black hole must have had a negative energy. With respect to an observer far away from the black hole. Okay. We might try to read this article next. This causes the black hole to lose mass. Where did it go though? Where did the mass go? I think this is like maybe I'm not actually really understanding what the black hole is if I'm asking where did the mass go. Excuse me, because it's not really there in the first place. It's not like there's really anything there. But like then where did anything go? Where did all the star stuff go? It just falls into this non-existent middle point. But then it also shrinks? Like stuff is still... It's... okay, anyways. It would appear that the black hole has just emitted a particle. It would appear, but it's not actually true. The particle just came out of vacuum flux. Like, that to me is a big difference. But maybe it's not. I don't know. In another article, oh boy, quantum tunneling, let's not even talk about that. This is some pretty crazy shit too. This is actually like a pretty relevant problem right now, like trying to understand this. So I would like to understand this at some point, because it has a lot to do with like quantum computing and even non-quantum computing. Yeah, like projected to create physical limits to how transistors can get. Because once you make transistors small enough, the jumpiness of the electron when it does its little quantum leap and like just completely like warps into another spot, basically, that can screw up transistors. If transistors are small enough, you can just warp to the other side of the gate, which is crazy. But no, this is for another episode. Let's ignore this theory. This is what we're sticking with. If we can understand this one, I'll be happy. Important difference between the black hole radiation is completely calling thermal radiation. The latter is statistical in nature, and only its average size sort of information, where the former fits the data better. It's information about the body that emitted it. Yes. So this is interesting too. This is something that a long time ago I talked to my cousin about, and it has something to do with like there's like a firewall. I don't know what that term really means, but I know that's the term they use on the outside of the black hole that's like keeping track of the stuff that's falling into it, even though the stuff that falls into it is just like gone. But black holes, yeah, like there's no way to tell what the star was made of after it collapses into a black hole. All that matters is how big it was, and if it was like rotating, and the charge. There's no hair. There's no like direction of the black hole. You know, this is confusing. I don't want to get too much into like the specifics of black holes because they're crazy. Okay, but what I mean, it seems weird. You can have like a, well, I don't know if you actually can, but imagine you have a star that's made entirely of like neutrinos or something. Okay, collapses, whoop, and then it starts emitting via Hawking radiation photons. Like photons are coming out of it. They're coming out of it, quote unquote, but there's no photons in it, right? There's, in the first place. So it's like, where did the negative energy particle, either the photon or the antiphoton, whatever happens to be captured, goes in there, and the mass shrinks, but it's not like the same thing is gone. Okay, yeah. So this idea of like information loss seems a little crazy. The black hole information paradox. It's nice that it's a paradox, because then it means that I don't actually have to understand it, because no one understands it. According to the conjectured, I don't know what that is. Black holes in certain cases, perhaps in general, are equivalent to solutions of quantum field theory at a non-zero temperature. Information loss is expected in a black hole. Permits no such loss. The radiation emitted by the black hole is probably the usual thermal radiation. Incorrect, and Hawking's original calculation be corrected. It's not known how. Okay, so this is what I was saying before. Far more cosmic radiation than it emits. Thermal radiation it emits. And yeah, this is something he talks about in Abhot too. That it could have been that in the long past of the universe, there were little tiny black holes that were actually able to start giving off more than they absorbed. And he kind of like speculates about what the heck happens once it totally evaporates. That's not clear to me either. Like once it gets to this point, okay, so it's like, where did my mouse go? We have this hole in space-time. At what point do you like undo the singularity? At what point is it small enough mass has radiated, quote unquote radiated away, that it starts behaving like this again, and light can start, you know, bouncing off of it and stuff, and regular blackbody radiation can happen. Because when that happens, it seems like the star stuff, the actual particles that constituted the thing that turned into the black hole, should like come back. Okay, but if it comes back, then what happened to the stuff that shrank? Where did it go? The stuff that when the negative energy came into it. So like maybe it doesn't come back? But that would mean it would like entirely evaporate, and that even when there was like only a couple particles left to evaporate, those particles would still have infinite curvature. Because otherwise we could tell what they are again. And then we would be able to be like, hey, there's some missing. When the wavelengths become shorter than the Planck... So the Planck length is like the grain of the universe. It's like the smallest measurement. Oh shoot, sorry, I forgot to... No. Switch back to this. I guess having the picture here is... the video is a little... no, that's not what I wanted to do. Hold on. There we go. Go like this. Oh, damn it. Alright, whatever. What was that? Oh yeah, the Planck length is, yeah. Time stops as measured from far away. Particle emitted from a black hole with finite frequency, if traced back to the horizon, must have had an infinite frequency. Therefore, oh my god. No trace back in time, as if image diverges from which it has a great distance. I kind of get it. Alright, you know what we should do? Maybe we should try to do this first. Oh, there is no simple English Wikipedia! Damn it. Maybe there's one for black holes. Oh, where'd it go? Oh. What? I didn't know to do this. Alright, baby. Oh yeah, give me that ESL treatment. Black holes have a temperature and emit Hawking radiation, which makes them slowly get smaller. Uh-huh. Okay, that didn't help a whole lot. So this is the gravitational lensing. So this again is because of this weird curvature thing. So you can imagine all of the photons that should be just showing us this nice clear picture of a galaxy are actually getting crazy distorted as they get all caught up in the black hole. Oh, excuse me. Quantum effects. These are the mass and energy of the black hole. It's therefore known as black hole evaporation. This happens in the virtual particle antiparticle layers. This is when one of the particles falls in and the other gets away with the energy mass. Because of this, black holes that lose more... What? No, but they don't... What are they losing? The other gets away with the energy slash mass. Alright, let's... We saw this one. This is where we start getting serious. Once we got the dot edu, we're like getting into it. We're in real territory now. Okay. One takes quantum theory into account. It seems that black holes are not quite black. They should glow slightly with Hawking radiation, consisting of photons, neutrinos, to a lesser extent, all sorts of massive particles. Massive here meaning, of course, they have mass, not big. In fact, they are as small as you can get. This has never been observed, since the only black holes we have evidence for are those with lots of hot gas falling into them, whose radiation would completely swamp this tiny effect. I like the language of this already. I like to use swamp. I like how clear they are, leading the sentence with "this has never been observed since." This is good science writing. So often people don't get that you need to bring out the purpose of the statement, like first and foremost. Anyways. Indeed, if the massive black hole has m solar masses, Hawking predicted it should glow like a black body of temperature. That's really, really cold. Only for very small black holes would this radiation be significant. Theoretically very interesting. Folks working on... folks. It's cute. Quantum theory and gravity fit together have spent a lot of energy trying to understand it and its consequences. Even idiots like me that are just reading a book because somebody died are spending a lot of energy on trying to understand it. Most drastic consequences that a black hole left unalone and unfed should radiate its mass slowly at first, faster and faster as it shrinks, finally dying in a blaze of glory like a hydrogen bomb. What? I kind of think in Abhot he says something like this. He's like, nobody knows what's really going to happen. I feel like it would explode. But explode with what? What's coming out? Wakarimasen! Okay, anyways. Total lifetime of a black hole M solar masses works out to be... That's a lot. That's like a long-ass time. People looked around for the death of small ones that can form the Big Bang, but they haven't seen any. So yeah, basically the idea is during the Big Bang, which is in itself a kind of a singularity, or it's like really the big singularity, and nobody really knows what's up. We do know that things must have been very, very close together and very, very hot, and from that we can speculate that really small black holes might form, and that if they did, oh sorry, I didn't scroll down enough. If they did form, then they might like be gone by now. Be gone, thought. Be gone, small black hole. And if they are gone, then maybe we can figure out how they died. But we haven't done that yet. You'll find Hawking radiation explained this way in a lot of pop science treatments. Yup. Yeah. Nice. Yay! Okay, this is what we get. Pop science. We're on pop science tier. Let's get into the real shit. Argument does not correspond in any clear way to the actual computation. At least I've never seen how the same computation could be transmuted into one involving virtual particles sneaking over the horizon. Last talk I was at on this, it was emphasized that nobody has ever worked out a local description of Hawking radiation in terms of stuff like that's happening at the horizon. Okay, so it's like generally, I guess it makes sense, averaged out over all of the ones happening around the entire black hole over a period of time. You can say you're Gucci. But I guess this guy at least. Who is this guy? John Bays. I think I've heard that name before. Isn't this guy's legit, right? Excuse me. Yeah, no, I think this guy is like a real one for sure. And this guy, I don't know who this is, but he sounds legit. Ooh, Fermions. That's a scary particle. What's that? I'm on Facebook. Anyways, okay. All right, so I'm gonna take this guy's word for it, I guess. At any rate, because he's gonna try to give us something else. Surprised this heuristic picture turned out to be accurate, but I don't see how you get that picture from the usual computation. Usual computation involved. This definitely looks like a made-up word. The idea is when you quantize, say, the electromagnetic field, you take solutions of the classical equations and write them as linear combinations of the positive frequency and negative frequency parts. These are particles and the other gives you antiparticles. Sure. The splitting is implicit in the very definition of the vacuum of the quantum version of the theory. One way and I do the splitting another way, or notion of which state. That doesn't seem weird. At all. Just kidding. What? The fuck? Well, again, it all comes down to like weird probabilistic stuff, right? Because with quantum mechanics, like I was talking about uncertainty and stuff, and it's like because you can't really know what's going on in terms of like where it is in this. You can only say with some probability. Okay. Thought of as the state of least energy. Really using different coordinate system of really different notions of time, hence really different notions of energy. Since energy is defined in quantum theory to be the operator H. Okay, so getting time involved. There's another part of Abhot that I just read that says some really crazy, interesting things about time. I don't know. Maybe I'll try to explain that. I'll explain that if it seems like it's kind of jiving with what this guy is saying. But let's try to just understand what the hell is going on here. Time evolution is given by exp minus ith. I don't understand what that means at all. I'm going to Google that. And we get StackExchange. So I think we're doomed. Time. Why isn't it at least bringing up this paper again? Why is it bringing up like a book and a bunch of math stuff? Alright, I give up. I don't know what this is. We'll just assume that maybe we'll figure it out later. It's quite conceivable that we'll have different notions of positive and negative frequency solutions in classical field theory. A solution that's linear combination of those with time dependence is called positive or negative frequency depending on the sign of omega, but of course this depends on a choice of time coordinate t. On the other hand, it's quite conceivable that we'll have different notions of the lowest energy state. Alright, sure. What's next? Now we're in a good old flat Minkowski spacetime. Oh, I love being in a good old flat Minkowski spacetime. You know, it's like when you lose game one and it's your counter pick, and you're like, take me to the Minkowski spacetime. I'm good on flat stages. Special relativity. There are a bunch of inertial frames differing by Lorentz. I think I've heard of this before. Yeah, this you can kind of like, I think you learn about this stuff with like relativity. Space-time. Here you can see it again. Satellite doesn't know where to go. I'm trying to go straight, but just go around and around. No. Okay, so like, shout outs to all you actual math people out there. I want to know this stuff. But I have such a barrier around seeing something like this. Okay? Actually, this one isn't so bad. I think I can understand what's going on here. This is the speed of light. And this is your like delta time squared minus your 3 space coordinates. The difference between them all squared. That equals 0. Alright? But then once you start doing algebraic steps, to be like, well, then of course that also means this, which is like taking the difference of the squares or something, and then it's like, oh, of course. I can only typically follow it like one line before my brain just starts shutting down, and this has been a big obstacle for me in trying to read a lot of things like this. So like, I don't know, like, is there a way to kind of develop this skill independent of just like learning how to do math? I kind of want to just learn how to do math, but it's, I mean, there's people that have spent the time I've spent on all of the other hobbies I've done combined on math, and even they are just like, man, I wish I could learn math. Okay, alright, let's give up on Lorentz transformations for now. Let's give different time coordinates, but one can check that the difference is never so bad. The different coordinates give different notions of positive or negative frequency solutions in Maxwell's equations. Nor will different people using the coordinate systems ever disagree about what the lowest energy state. So all internal observers agree about what's particle, what's an antiparticle, and what's the vacuum. Alright, I'm happy with that. I don't know if maybe I understand. Because, like, I already assumed that. I already assumed that we could work that out. I guess I had just kind of taken it for granted, but I guess you should never do that when you start talking about quantum mechanics. But we've arrived back at that, so great. Here space-time, there aren't these best coordinate spaces in the inertial ones. So even very reasonable different choices of coordinates can have different agreements about particles versus antiparticles or what's the vacuum. I guess we should look up this. Oh god, isomorphism of... No, it's just math! Bring me back into space! Also important for understanding the Hawking radiation! No! Alright, let's really try to do it. Consider the canonical... Fuck, what? Bosonic creation and annihilation operators in the harmonic basis. A with hat and A with hat and dagger. Armed A. Trust no one, not even yourself. This coordinate system, I guess, is 1. Define a new pair of operators where B is U and V and B with a knife. Wait, what? How are these... Why is there an asterisk here but not an asterisk there? Isn't asterisk just means times? Or does it mean like cross product or something? But they can't be cross product or whatever because these aren't like vectors. They're coordinates within a vector. Shouldn't they just be scalar numbers or something? Okay. How long is this video? We'll give it an hour and then we'll assess if we've made any progress. Oh god, no, this is hopeless. And stuff like this too, because I don't, like, I know kind of what cos and sine are. I kind of remember, like, I can picture that circle in my head and it's making the triangles as it spins around, you know that one? This guy, this one's pretty good. Or this one. That makes sense. But it's like I don't just like snap to this. I don't snap to any intuitive understanding. I would have to like look at this for a while and look at these for a while and then like maybe I would get what was going on. Or like what? I know this is sum, but usually there's a bunch of other numbers that help you figure out what you're summing. But what is this guy? Giant pi. God. What does it mean that it's AIK? What does this mean? It's like... This has something... Okay, so it's like it for... I did know this at one point. This is like for any I, there exists AI such that it or 0, it to 0, but not like over 0 or something. Alright, whatever. We're giving up on this. We gotta keep plunging through this. Okay, these are whatever Okay, so there's a black hole around. One day we can split solution of maximum equations in the positive frequency in the most blitheringly obvious way that someone far from the black hole in the future would do it. Split solution of maximum equations in positive frequency in the most blithering obvious way that someone far in the past, before the collapse into the black hole has happened, would do it. Okay. Neither of these seem blitheringly obvious. I guess the blithering obvious one from far away is that we would say the positive one, the positive energy is the one that's coming out. The negative energy is the one that's going in. Right? Which is what we labeled here. That seems obvious to me. Maybe that's what they mean? But I don't know what this one is. Is that like the opposite or something? Because it's like... But then, if we're doing it before the black hole showed up, then... Okay, then it's just like 0, isn't it? Because they just annihilate, and then there's no net change in energy either. Additional things to say about the guy far in the future and far away from the black hole can't see what's in the hole. This is incomplete information about the state, so he stays a state with entropy, in fact, a thermal state. This black hole is not internal, so the guy way back in the past didn't have the black hole to contend with. Pairs of particles and antiparticles. So in the end, we're basically just where we are at the start. He hasn't like advanced my heuristical explanation of it. At first he was like, this seems to be inconsistent with the math, which I don't understand. And then at the end he's like, ahaha, it turns out it probably is consistent. All right, let's try again. Black hole theory and Hawking radiation. Ooh, somebody asked on StackExchange. Let's see what people said on StackExchange about Hawking radiation. No, I'm already past this guy. Yes, we're past somebody. Yeah. Right. Oh. What? Okay. Ooh, okay. Quantum jitters that occur near the event horizon of a black hole, which create both positive energy particles and negative energy particles, radiation. I understand why only the negative energy particles are being absorbed into the black hole, while the positive energy particles shoot outward. No. Okay, so this is like... it's not this. It's that you're defining it. That it has to be the positive one goes out and the negative one goes in. It's not that they're pre-assigned positive and negative energy in the pairing, right? It's just a particle and an antiparticle. Both of them have positive energy for the brief existence they have before they annihilate. Okay, but maybe there's an answer to this, that particles being swallowed explanation is a metaphor and is actually how the calculation is done. A pair of virtual particles are produced and there isn't a negative and a positive energy particle. Yeah, it's possible to distinguish between them. The Taylor system can interact with the black hole and split. The interaction guarantees the emerging particle will be a positive one. Yeah. NB, not because? Wait, what? NB? This is some crazy StackExchange acronym that I don't know. Or initialism, sorry, not technically anachronism, unless you say it as MB. Positive and negative doesn't mean particle and antiparticle. Right. Black hole will radiate equal. Right. Okay, so I understand all this. You quantize a field, you get positive frequency and negative frequency parts, representing particles and antiparticles. Positive and negative frequency are defined depends on your choice of vacuum. Quantum field is unambiguously defined. Like the region near black hole. So this is what this one was talking about, right? They just, yeah, this is quantize a field. You get positive. Okay. Excuse me. This is largely incomprehensible. Gives the UNRRA effect. Yeah, but okay, well, it's not an antiparticle falling into the black hole. No, it's either a particle or an antiparticle. It doesn't matter. It just has negative energy, which is like what? What? Here, space-time, there isn't an unambiguous choice of vacuum. There's an unambiguous choice only when you have a Hamiltonian. And this only happens when the time translation is an I. Oh, fuck me. There's exciting disagree about the particle content of the system. When falling freely into a black hole, we'll see empty space. While an observer off at infinity will see a space filled with blackbody radiation. So this has to do with the section I alluded to in Abhot that I recently read, but I don't think this is a very good explanation. Um, I'll pull it up in a second. I sent pictures of my Kindle to my friends because this part hurt my head badly. Okay. This is actually so absurd. We're looking at a picture of my Kindle on the computer and recording a video about it. Explanation of how black holes can emit particles and radiation given in Chapter 7 was that one member of a virtual particle-antiparticle pair, say the antiparticle, might fall into the black hole, leaving the other member without a partner with which to annihilate. The forsaken particle might fall into the hole as well, but it might also escape from the vicinity of the black hole. If so, to an observer, a distance would appear to be a particle emitted by the black hole. One can, however, have a different but equivalent intuitive picture of the mechanism for emission from a black hole. One can regard the member of the virtual pair that fell into the black hole, say the antiparticle, as a particle traveling backward in time out of the hole. When it gets to the point at which the virtual particle-antiparticle pair appeared together, it is scattered by the gravitational field into a particle traveling forward in time and escaping from the black hole. If instead it were the particle member of the virtual pair that fell into the hole, excuse me, I gotta get the next page, which I also took a picture of. This is what this channel is like now, you know. No more manga. Only this. only until we understand quantum theory. Just back in time and coming out of the black hole. I should have kept, sorry. Particle member of the virtual pair that fell into the hole, we can regard it as an antiparticle traveling back in time and coming out of the black hole. The radiation by the black hole shows that quantum theory allows travel back in time on a microscopic scale, such that particle can produce observational effects. I don't get it. This part also doesn't really make much sense to me. And he talks about time travel a lot. It gets really crazy. But there's a part where he's talking about the thermodynamic arrow of time, which is where entropy always increases, that things will always go from disorder to order, and even if you use energy to produce an ordered state, the energy that you use, which is dissipated as just kind of noisy heat energy with no order whatsoever, is greater than the order you create, which is just like a general, sometimes very existentially depressing rule about the universe. So he says that time goes in that direction, that pretty much what we think of as time is actually just that effect. So that like our psychological understanding of time, our sensation that time is going forward, is just our brains constantly creating disorder. It's like our memories are a process by which we create ordered information, but of course the energy we expend in remembering something is greater than that. And it's like that effect we can't like reverse. We can't somehow like get energy back by forgetting things. So therefore we're always like remembering forward in the entropy direction. So that was like very mind-blowing when I kind of wrapped my head around that. I hope I explained it kind of well. And that like outside of that phenomenon, outside of that sensory phenomenon, like we can't really say that time exists in the way that we think of it. So that I guess if you're like in a black hole, if you're already past the event horizon, you're in a place now where like that doesn't hold. Like negative energy means that like does time kind of start like running backwards inside of the black hole? Because there's another part where he talks about what the sensory experience of going past the event horizon would be. And there it also involves time-space relativity, where like as, you know, like the theory of relativity, that as you accelerate, you become more massive, your energy goes up, your massiveness goes up, and your time slows down. It's crazy, but we know that one. That's a pretty common one. It's a way to kind of try to explain time travel in a lot of sci-fi. um, and there's like the twins paradox and stuff. You age slower if you're flying in a spaceship going around the Earth than you would at home. Anyways, so it's like as you fall into the black hole, you get more and more and more massive. So time gets slower and slower and slower. And as you approach that like asymptote, time stops. So therefore then also thermodynamics and increasing entropy stops, which I guess makes sense because the black hole can't really go up in entropy because there's no like information, there's no like order or disorder with it. It's just this like one singularity state. Okay, so then something with like negative energy. I thought I was kind of onto something there. I kind of felt like I was understanding it for a second. What was the last one we were reading? We were reading these StackExchange ones. Okay. Saps energy from it. Saps energy from it. Stealing energy from the black hole to emit radiation from just beyond our memory. Okay. Right. Big bag. It's just a big bag. Okay. Okay. Alright, we've been at this for over an hour. Maybe we should give up soon. Let's check out one more link. This one? Maybe we should watch a video. I don't know. Oh god. Schwarzschild. I like the fact that we call them Schwarzschild black holes. It's literally like black child. Oh wait, no, is it? Swart? Or is that Schwartz? With a z instead of a Schwartz? Schwartz. Yeah. Anyways. Excuse me. Black hole, spin. Okay. Space-time cannot be continued, and classical relativity breaks down. Yeah, so this is all covered in an app hot. I got that. Okay. Yeah. Uh, Ooh, this is a nice picture. So you can see they're pooping in and out all over the place. And then, oh, we're gonna make another one here. Oh no! My buddy, I just want to annihilate. Where are you going? I will go look for you. Uh, Gravitational field around. Okay. Escape. Observed as thermal radiation emitting from the black hole. Negative part, say positron with negative energy. Positrons don't have negative energy and negative mass, though. The positron is just the antiparticle of the electron. It doesn't have negative energy. It's just on the opposite wavelength, right, of the positron. Or like the spins interfere or something. Such that they annihilate, such that they cancel each other out. Nah, it's too hand wavy. Because it doesn't intuitively have, would they say a positron with its negative energy? I think that's like a bad implication. It's going to confuse people. Black hole would gradually lose mass. But it's not, like here, so for a while, I kind of thought, oh, maybe what it is that it's going into the black hole and it's always annihilating with something in the black hole, right? And that way it loses mass. That it's like the black hole is just the soup of whatever antiparticle or particle you need to annihilate with whatever particle or antiparticle happens to come along, and in that annihilation it shrinks. But no, that's not what's happening at all. That would be nice and simple, but no. Because it's not that it annihilates when it goes in. It just has negative energy. Information paradox, a Hawking paradox, whereby physical information, things identity, properties of particles going into the black hole appears to be completely lost to the universe in contravention of the observable laws of physics. Right. Defended this paradox against the argument of for almost 30 years. Fermions are tragically exclaiming two phenomena more. Wow. Not contained, although perhaps not in our universe, but another parallel. No, Stephen Hawking, settle down. I mean, all right. Just before we finish, because I don't know this paper is going to get us anywhere, and I don't want to dive into another one. I'll say some crazy things about parallel universes that don't really make any sense to me. So I read a while ago Scott Aronson, quantum computing. This, if you're interested in quantum computing, I highly recommend this. You can find it pretty easily by just Googling what I Googled. A friend of mine took this course, and he said it was great, and he said that I should read these notes, even if I don't understand the math, and even if I have no clue how to do the puzzles, that I would still really get something out of it. And I really did get something out of it. I think I really understand quantum computing a lot better because of it. So check this out. This one especially is a banger. There's a lot of the anthropic principle is basically like, okay, we now, you know what, I'm not even gonna start. It's kind of hard to get your head around it. We'll do one fun thought experiment that I learned from these notes. Okay. We're going totally off topic now, by the way. Oh yeah, I should finish though. Before we close things out with this fun thought experiment, what I was going to talk about here is maybe it was in here. Anyways, there was a part where he's talking about Shor's algorithm. He also has a really good paper little like layman's explanation on Shor's algorithm. I think this one. I'm not going to try to summarize this word right now. But he quotes some guy that's like, and I found this quote like chilling, that it's like, okay, if there's not parallel universes, where is the work of Shor's algorithm being done? Like, where is it actually happening? And I don't know. I can't capture why it was so chilling, but all right. Anyways, let's do this fun thought experiment on the anthropic principle. I kept thinking anthropomorphic principle, which is the principle whereby you can take anything and make it into a human-like thing, and then someone else will draw porn of it. No, the anthropic principle. Okay. So this is kind of a fun way to kind of get your head around it. So there's this guy. He's like a serial killer. And he wants to play this like really demented game. So first he kidnaps one person. Okay? And he blindfolds them. They don't know how many people have been kidnapped. They just know that they've been kidnapped. And he's like, I'm gonna roll dice. And if I got snake eyes, these are some excellent cubes. That was a little better. If I got snake eyes, you die. You can tell I read a lot of One Piece because I knew how to draw this so expertly. If we get snake eyes, if we got 2 1s, you're just dead, man. Sorry. But if I get anything else, any other combo, this is probably unnecessary to draw pictures and stuff. It's just fun. Whatever. Any other combo, free to go. Free. And if you're free to go, what I'm going to do next is kidnap 10 people. So this is round 1. Let's say he doesn't get snake eyes. Next time, it's 10 people. Okay? I don't know. It's 10. And he gives them the same bargain. I'm going to roll these dice. If I get snake eyes, you're all dead. I'm going to kill every last one of you. And if not, I'll set you all free. And then I'm going to get 100 people. And it's different people. He'll never kidnap somebody twice. And this goes on and on and on. Until he finally gets snake eyes and kills everybody. Okay? Once he kills everybody, he's done. He's got it out of his system. He's just going to stop. If you don't like how grisly this is, imagine instead he gives them $1 million each. Alright, so you've been kidnapped. Your blindfold is on. You have no idea what round it is. How many other people have been kidnapped in the same round as you. How many rounds there have been. Whatever. You don't know if you're going to get killed. If you're going to get the $1 million. Whatever way you want to think of it. Or if you're going to go free. Okay? The question is, what are your odds of dying or getting the $1 million? What are the odds? One way to think of it is that it's like 1 in a 36 chance, right? There's 36 different combinations of 2 dice, and only one of them is snake eyes. So you have a 1 in 36 chance of dying. The other way to think of it is that when he finally kills somebody, if you think of like the population of people being kidnapped as like going up, when he kills somebody, when it's finally like the death time, it's going to be the biggest chunk by like a big factor. So if you just happen to land anywhere randomly in this curve, it's most likely going to be like right at the end. This isn't growing as quickly as it actually does if it's an order of 10 every time, but whatever, you get it. You're much more likely to be like in this category than one of the few people like over here, right? Like if you just kind of picture yourself blindly throwing a dart at this chart, much more likely to hit this. In which case, if you think of it like this, the odds seem to be 10 out of 11. Because let's say on the 10 people, he hits Snake Eyes, all these 10 people die. That means that if you were just one of the 11 people kidnapped in the entire experiment, there's a 10 out of 11 chance you're going to be one of these unfortunate people rather than this one lucky guy. Same with if it happens at 100 people, there's 11 people that have gone free and 100 people, well, I guess, wait a minute. Yeah, 100 people that die. So you're, again, much more likely to be part of the 100 than part of the 11. So this is where it comes down to the anthropic principle of like, when we exist, our own conscious experience, is it like we just kind of randomly happen to be in any given body and any given circumstance, or is it that like because we exist, I don't know. Anyways, have fun with this one. It's a bit of a mind bender. Which one is it? I don't know. No one knows. See, the thing though is like you can't really meaningfully say the odds are this or this, right? Like you can't meaningfully say like probabilities don't really exist because it either just happens one way or the other. So in some sense, it's not really a question you can ask, but in another sense, it is a question you can ask. I just asked it, and I don't know. And it's like you can't, for other like really mind-bending probability problems like the Monty Hall problem or something, even though there's kind of an unintuitive answer at first, you can very easily prove it to yourself just through experimentation. But here, of course, you can't prove it through experimentation. You can't just like live over and over again and see what the odds are, because it's like dependent on anyways, this concludes episode 1 of the new channel format. A learning channel. I hope you learned something. I kind of think I learned something. I learned that it's a lot more complicated than I thought it would be. What I was hoping is that I would just find some blog that had some explanation that's like, oh, it has negative energy, excuse me, because of this. It's like, oh, okay. But really, it has to do with this idea of quantizing the vacuum flux and the way that, depending on your observational point, the parts that you think are positive and the parts that you think of negative are going to be different. And that's like really far away from something I can understand the meaning of. So I don't think we're ever going to figure out negative energy right now, at least. Maybe in like 25 other episodes we'll figure it out. But I think I got a little closer just because I can kind of understand that. And for a second there, I thought I was kind of getting something with this idea of like negative time and the arrow of time getting flipped around because the thermodynamic direction got flipped around or something. But I can't really put it together. Anyways, the next episode will be easier. Next episode we'll take a break and do something easy. So look forward to that.